எக்கோ ஆகுதுங்க சார்.
ஓகே, இப்போ சரிச்சுங்களா?
இப்போ ஓகேங்க சார்.
Rahul sir, shall we proceed?
Yes, sir.
See, sir,
Can you?
please start.
Yes, sir.
Okay. Start.
Good morning to one and all present here. With great joy and immense excitation, I feel privileged to extend my warm welcome to all presented here for the second day of 3 days FDP conducted by the Department of Electrical and Electronics Engineering and Association of Electrical and Electronics Engineers. I cordially welcome Dr. C. Vivekanandan sir, Professor and Head of the SNH Department, Dr. NGP Institute of Technology, Coimbatore. Participants, our mathematics professor, Dr. P. Sendil Kumar, has passed away due to COVID. Let us take a moment to pray for his soul to rest in peace. For a minute, I would request everyone to stay quiet. Thank you all. Now, I kindly request Dr. S. Jagannathan, Professor and Head, Department of Electrical and Electronics Engineering, to say a few words.
Thank you, Karanya. So, very good morning to all for this second day faculty development program. So, today's session will be a wonderful session handled by Dr. C. Vivekanandan sir, Professor Head and Senior Professor of our college. He's a person, he's a kind-hearted, supported person. He's a expertise in electrical field. So I think today session will be a lot of informative sessions. I wish you all for this second day session. So Karanya, please take.
Thank you, sir. Dr. C. Vivekanandan sir, who is a professor and head of the SNS department, has completed his bachelor's degree, master's, and also PhD at Coimbatore Institute of Technology, Coimbatore. Sir has a cumulative experience of more than 30 years. He is also awarded with Excellence in Teaching by the Lions Club of Coimbatore. He has also published more than 36 international journals, 7 national conferences, 20 international conferences, and 10 consultancy projects. Now, I kindly request Dr. C. Vivekanandan sir to take over the session.
Thank you, Karanya. Highly respected head of Triple Department of Dr. NGP Institute of Technology, Dr. Jagannathan, convener of this FDP, Dr. K. Ramash Kumar, coordinators, Mr. R.B. Silva Kumar and Mr. J. Rahul Kumar, beloved professors from other institutions. Very warm good morning to one and all. So, though I am basically an electrical professor, presently I am serving as head of the Department of SMH at Dr. NGP Institute of Technology. And Dr. P. Sendil Kumar, who is associated with me for more than 5-6 years, even more than 7 years, right from SNS College of Technology. We are working together at Dr. NGP for the past 2 years. He is my best companion because he is a bit closer to my age, comparing others. They are all very young chaps. He is a bit closer to my age. So he was my best companion at Dr. NGP, and we were sharing a lot of things every day. Normally, we meet in the morning by 8:30 at in my room, and we have some chat for about 15-20 minutes about all issues, politics, academics, students, family, and a lot. And he reported some cough and fever before just before a month, and he was admitted in a local hospital there for about a week or 10 days. He developed breathing issues, respiratory problems. So he was then admitted into ESA hospital. Until then, till he was admitted, even after, after admitted in ESA hospital, we send messages through WhatsApp, and once in a while we talked over phone also. And after 3 or 4 days at ESA, her doctor called me. Her daughter called me and reported that he was so critical. So he was immediately shifted to KMCH with the help of our benevolent madam, Dr. Daumani Palaniswamy. He was admitted in KMCH, and he was in ICU for about 10-15 days. And he was given first-class treatment by doctors of KMCH under the guidance of our respected secretary madam. But unfortunately, in fact, before 3 days, I was talking to her daughter. She said that he was improving. But unfortunately, this morning, the message came that he is no more. It's a great loss to me personally, and loss to the academics. He is a very good professor, a kind-hearted professor. In fact, I wanted to refine my presentation this morning, but I couldn't because of this. So with the grief stricken and heavy heart, I'm handling this session. If you struggle, if you fumble in between, please bear with me for the known reasons. So let me start my presentation.
Yes, sir. Rahul sir, please remove one presentation. Rahul sir?
Sir, I'm presenting, sir. Please.
Rahul sir, remove. He is presenting, sir.
I think I have come, sir.
Yes, sir. I stopped the screen from one.
Okay. Thank you, sir.
Okay. Good morning, everyone. So at outset, I thank Dr. Jagannathan and his team for bestowing this wonderful opportunity to be amidst you and to discuss something about the state feedback control and its application in power electronics. So most of my presentation today will cover state feedback control, which is a generalized one. This is not applicable not only for power electronics, this is applicable for every engineering field, right from robotics, mechanics, design of systems, and control of torque and whatnot. It is applicable for almost every system, including economical, social, plenty of systems. Okay. So let me give you an overview, a bird's eye view on state feedback control first, and go for a simple application in power electronics. My plan is to present the application of state feedback control in single phase H bridge full wave rectifier, full wave inverter. Okay. So coming to systems, as an engineer, we in general want to expect a system to meet our specifications, to meet our needs. Specification means our needs, right? To meet our needs. So, in general, for every engineering system, we have got some specifications. We, in general, analyze a system either in time domain or in frequency domain. This state model is a pure time domain analysis. So, let me talk about the time domain specifications. So, the first time domain specification is race time. I'll come to the later. What is race time and peak time and all. Of course, you may be knowing this. Nothing wrong in overdoing it. Peak overshoot, settling time, and steady state error. These are all the major time domain specifications. I can even say this peak overshoot, settling time, and steady state error. Last three are the major criteria in designing your time domain system. And whenever we design a system, we want the system to be stable in the sense it has to work as we expected as per our design, and without getting stalled or without getting exploded. Okay, so the system should not die or system should not misbehave during the operations. So that's called system stability. And there are some specifications on system stability. It is called absolute stability, marginal stability, and conditional stability. And we have, of course, bibo stability and other stability aspects, which we will not go into that because our concern is only about these things as far as power electronics or our engineering design is concerned. So absolutely stable in the sense the system will be stable with respect to a particular parameter, irrespective of the value of the parameter. That parameter may change from 0 to infinity. That parameter can take any value, because when we talk about parameter, it can be only a positive value. So it can take any value between 0 and infinity. The system should not malfunction. Okay, whatever be the value of the system should behave as per our design and as per our requirement. And that's called as absolutely stable. And second one, marginally stable. Of course, the first one is never possible. You know, if you take a resistor, if you take a voltage source, and if you take a current, you can never expect the resistor to behave normally, irrespective of the applied voltage. At one stage, it will burn out. Okay, so absolute stability is only a theoretical criteria, so that's not there. Marginally stable is the system is said to be at the verge of stability. We cannot say the system is stable or system is unstable. So it is like something like cat on the wall. Okay, so it may jump either this side or that side based on the environmental conditions and perturbations in the system parameter values. And coming to conditional stability, which is by and large is a practical stability, conditional stability. A system will be stable only for the predefined range of that parameter. Okay, the parameter value exceeds that, or if the parameter value comes below this, the system may not perform as per your design specifications. Okay, normally when we design a system, we linearize the system. Okay, all the systems are highly non-linear. We design for the system to operate around an operating point, and we linearize the system around the operating point. So as long as the system parameters are bounded between this linear range, upper bound and lower bound, the system will behave as per your design or as per calculation. And once it overshoots or undershoots your predefined values, the system may behave erratically. The system may malfunction, the system may even collapse. Okay, I can recall that OCC, what we do for our DC shunt generator. Normally what we do, we draw a OCC curve, which is an exponential curve, and we draw a tangent which is passing through origin. Okay, so the objective of trying that on the tangent which is passing through origin is we are trying to linearize that. Okay, the system will behave linearly about certain range. I cannot draw it because I have no specialist to draw. So you can recall. So that that straight line will align with the graph only for a certain portion. Okay, so based on that only we go for speed control of thing or torque control or whatever it may be. Okay, so as long as your system works within that range, your output will be satisfactory. Once the operating range overshoots or undershoots that range, your system will not behave properly. So that's why it is conditionally stable. Within that range, the system will perform properly. So all our designs, all our power electronic designs, are in general, all our engineering designs, will come under this conditional stable category only. Okay. And if you talk about stability, and in control system point of view, the stability is based on the location of the closed loop poles. Poles, the roots of the denominator polynomial of the mathematical model of your system. Okay, whatever be the system, as an engineer, we develop mathematical model for that. For example, if you take this equation, r into I plus L into di by dt plus 1 by c integral I dt equal to V is the mathematical model of your RLC series circuit. Likewise, we can develop the model for any given circuit. It may be a simple equation or more complex equations. Maybe some 5-10 equations that will describe a single system. That depends on number of components involved, number of energy storing elements involved, and the complexity of the system as well, I can say. Okay, so if you take those mathematical models and if you take transfer function model, what we do, we write output Laplace of output variable divided by Laplace of input variable. Laplace of input variable. That then we get a numerator polynomial and denominator polynomial, and the roots of the denominator polynomial are the poles of the system. And the poles, the location of the poles determine the stability of the system. And when all the poles of the system, the system may have 3 poles, 5 poles, or 10 poles, even 20 poles. That depends on the complexity of the system. What will be the number of the poles? If the poles are located on the left side or the negative side of your real axis, or if the poles have a negative real value, then the system is stable. Otherwise, the system is unstable. Okay. Let us see the response of the systems. Let's talk about only the poles which are lying on the left of a S plane. Because once you take the poles which are lying on the right of a S plane, it will be e power t, e power at, for example. So e power at, when t increases, that the power will increase. So it will reach infinity. So e power infinity will be infinity. And on the other hand, if the poles are on the negative side, it will be e power minus at. So when t increases, it will approach minus infinity, which is 0. The system is stable. Okay. So if you take only the poles lying on the negative of cycle, the left side of the S plane, you have real axis poles. That is, the poles will be on the real axis. And what you see on your right top is the impulse response of that poles. Okay. And the second one, the poles may be at origin. So the poles may be at origin. It is a bit tricky issue, poles at origin. Okay. And the simple response of the system will be like this, will be exponentially falling down to 0. This is impulse response. And if you take complex conjugate poles, poles are complex conjugate pairs, because whenever the poles are complex, it will be a complex pair, complex conjugate poles. The impulse response will be oscillatory, as we see the third graph. Okay, on the screen. And again, another criteria which defines the system performance is how the system response will be with respect to time. Okay. Again, this depends on the type of the poles. Okay. There are 3 types of dampings. A system may be critically damped, system may be over damped, or system may be under damped. Okay. Let me see the graphs of those systems. The blue one, that is data 1, what you see right now on your screen, is under damped system. The immediate next one, which is below that, data 2, is overdamped systems, and the last one is underdamped systems. Okay, which system we will choose? Because all these depends on the location of the poles. Because when you take your oscillatory response, the poles must be complex conjugate. When it is critical response or it is overdamped response, the poles must be real. Okay, on the real axis, on the sense imaginary part. And which type we will select. And if you select the last one, underdamped, if you see the system response is so slow, the system is so sluggish, and it takes longer time to reach the steady state. I'm sorry. Longer time to reach the steady state. Okay. So the system is so slow. Okay. And if you take the one which is on the middle one, the system races sharply and it reaches the final value, the steady state value, in lesser time. Comparing this, this is the faster response, right? The middle one is the faster response. It is reaching the steady state value earlier than the other two systems. And if you take the third system is bit oscillatory, and it is certainly it is better than the third one, but it is not as good as the middle one. Okay, these three responses what normally we have. So if you want to, which one you will choose? All these three are possible practically. I'm talking only about a stable system. So all these three are possible for a stable system. So which response we will select is the big question. Okay. So if you take this middle one, this critical response, it is very difficult, practically very difficult to achieve this critical response, because if you take your RLC series circuit, your critical response, which is controlled by the damping factor, is a function of your resistance, capacitance, and inductance. So unless otherwise you are able to select the proper values for your R, L, and C, you will not be able to achieve this critical damping. And even if you are able to achieve exact values that are required to achieve this critical damping, it may not be constant due to environmental conditions. Maybe the moisture in the air, or the temperature, environment temperature, or other factors will influence these values, and there will be a drift in the values, so that your system will be no longer critically damped. You remove either upper or lower. Okay, and the third one, or which one is the top, is underdamped, which is oscillatory. But as long as these oscillations are well in control, we can accept it. So for these reasons, all our practical systems are underdamped systems. Doesn't mean all systems are 100% underdamped. We do have systems with overdamped. For example, if you take your lift operations, or if you take your door operations, these are all under this underdamped operations, sorry, overdamped operations, where the response is supposed to be very sluggish or supposed to be very slow. Okay. And so what they have concluded is a system must be underdamped. Okay, even in power system also, or in your power electronics also, we design the system to be underdamped. And in this concept, say a system may not be containing only your complex poles. A system by nature, inherently, it may have complex poles. It may have poles at origin, or it may have real axis poles. As I said, we are concerned only about the stable systems. Okay, so for a stable system, we have plenty of poles. And for example, if you take a complex poles, it will contribute this oscillatory nature during your transients. And if you take your real axis poles, they will contribute the exponential response during transients. And so your transient response of a system is the algebraic sum of these individual contributions. Okay, so a pole may give exponential response. A pole per complex pole pair give you oscillator response. There are 2 or 3 complex poles. They will give 3 different oscillations, and your final response of the system will be the algebraic sum of those responses at any given point of time. So if this is the case, we cannot decide how the system should respond, because when we try to adjust one, the other pole may get affected. And when their poles are much closer to each other, the response will be so clumsy. So we may not, it is very difficult for us to decide how our system to respond, or rather how to make our system to respond as per our specifications. So that's why we get into the concept called dominant poles. Okay. So these poles, dominant poles, the stable systems, the poles will be only on the left of a S plane. We have several poles on the left of a S plane, and the first condition is the dominant poles are the poles which are closer to your imaginary axis, which are closer to your imaginary axis. Okay. So poles which are closer to the imaginary are called, or maybe the dominant poles. With the condition, the second condition is displayed over here. So remaining poles, okay, should have the real part at least 5 to 10 times that of your pole which is closer to your imaginary axis. Okay. So unless there is this condition satisfied, you cannot claim that the pole which is closer to the imaginary axis as a dominant pole, because the other poles which are closer to that may also provide dominant responses. Okay. Now let us take this example. So there are two poles which are real axis poles, which is one pole is at -2 and one pole is at -10. Okay, we have two poles. And know this, yeah, the pole which is at -2 is a dominant pole as far as this is concerned, because the next pole is at -10, which is sufficiently farther away from your first pole. Okay, let us see how the system behavior and why we call this as dominant poles. Okay, now let me open the file which I have created for this. Now I think you can see a file. It is a MATLAB command window what I have opened, and you see I have defined this first system, which is G1. This is my system what you have seen, which is given by 1 by s plus 2 into s plus 10. This is the pole system what I have defined, and I have taken the response of these two poles independently. So for first pole, and if you do a partial fraction and all, the residue of the first pole is 1 by 8, and that of the second pole is -1 by 8. So the first pole is -1 by 8 into s plus 2, and the second pole is -1 by 8 by s plus 10. Okay. Now let me run this, and let me load these things. So the it is run. Let me view its response using the LTI viewer. So LTI viewer is getting loaded. Yeah, it's there. Now let me import those two systems here. So this is G1, all the systems, G11, G12, that is subsystems, and G1 is the overall system. Of course, now you can see three graphs on your screen. Okay, the red one, the blue one, and the yellow one. And let me add the legend so that you can understand. Yeah, we got the legend. Okay, so the blue one is G1, that is your first or the overall system, right? And the red one is G11, that is your what is G11? G11 is this one, right? Your the pole which is closer to your your imaginary axis. And G12 is the pole which is farther away from the imaginary axis, whose response is given in this yellow line. Okay, is it yellow? So it is yellow line. Okay. Now, if you see, the blue response is the overall response when both the poles are acting together, and the red response is the response only when the first pole is acting, and the yellow response is the response only the pole which is farther away from your imaginary pole is acting. And you see the response, the actual response is much closer to your this response, which responds this pole which is closer to your imaginary axis. Okay, and if you see the transient response, the transient is up to this. I'm right. Let me add. Settling. So settling time. So the duration from this, say this to this, is the settling time, during which the transient is purely dictated by this red. I'm right, because this yellow, the oscillations in the yellow has died off after say 0.4 seconds, whereas the transient is extended up to around 2 seconds. So the transient of the first one, the pole which is farther away from the imaginary axis, dies out at 0.4 seconds, and from 0.4 to 2 seconds approximately, the transient response is completely under the control of this the red, which is your system, which is closer to your imaginary axis or the dominant pole. Okay, so the transient response of the system is completely dictated by the pole which is closer to your imaginary axis than the pole which is further away from the imaginary axis. But of course, you know, the settling time is settling time is 4 by zeta omega n or 3 by zeta omega n. Let us take this 4 by zeta omega n for 95% category, 98% category. So this 4 by zeta omega n, this zeta omega n is the real part of the pole. Am I right? It may be a complex pole, it may be a real axis pole. The zeta omega n is the magnitude of the real part of the pole, and your settling time depends on the real part. It is 4 by zeta omega n, or the settling time is inversely proportional to the real part of the poles. Inversely proportional to real part of the poles. So if you take this pole which is this G12, for which it is 10, so it is 4 by 10. So that is the settling time. 4 by 10, what is the settling time? Let me check it. It is 0.4, am I right? Approximately at 0.4 it settles. And if you take this, it is 2 by 10. So it is 2 by, sorry, it is 1 by 4 by 2. It is 4 by zeta omega, and it is 4 by 2. So approximately at 2 seconds it settles. Am I right? Approximately 2 seconds it settles. Okay. The transient response, because as a system engineer, we are very much concerned about the transient response than our steady state response, because during transients, if you take, even if you are simple RLC circuits, RLC series circuits, the please hold on, one moment. Sorry for the interruptions because I had a call from Sindhul Kumar's daughter, so I had to attend. Very sorry. So coming back to our discussions, so coming back to discussions, so the entire transient response is dictated by the pole which is closer to the imaginary axis. Okay. So that's why it is called dominant pole. Dominant means its contribution is dominating during the transient response. That's clear from this figure. Okay, let's go back and continue again. So that's what this. And again, when you take this, this is a bit of a tricky case, which is what we are very much interested, because as I said earlier, we design our system to be more transient or oscillatory than the exponential response. Unless or otherwise it is demanding, we never go for this sluggish or exponential response. We design only with the oscillatory response. So let's take an example with a system with a pole which is a real pole and another pole, a pair of poles which are complex conjugate. So when we do partial fraction, we get this. This is for the first part or your real axis pole, and this is for the complex pole. And we'll see how the response of this system. And let me go and load this example 2. Okay, so I have defined the first system, which is the overall system, which is called G2. That is example 2. That's why I defined it as G2. This is 1 by s plus 10 into s square plus 2s plus 5. And this is the first part of this subsystem, or first subsystem, which is having only the real part. And this is the section which is having only the complex poles. And we'll see how the system behaves for this. Okay. And let's load those systems, all the 3 systems, and we'll see how the response is. Okay. So let me get the characteristics. Let me take the peak response. Settling time. Because I'm sorry, this is running on the previous. I'm sorry, for example 2. Let me run this. Let me run this first. Run. Let me take G2. Please wait. Okay, let me take G2. Please wait. It's capital G2. So the system is there. So G21, G22, G21, yeah, G22. So we have this complex pole and real axis pole. Now let me go and do this analysis. Help you here. And if you see, let me load the systems, import all these 3 systems. And let me get the characteristics. Peak response. Stage time. And let me have the component legend. So again, there are you can see 3 responses. The first one, the blue one, is G2. That is the oral response. What you see on the topmost is the oral response. The middle one, that is G21, which is in some sort of a brown color, right? A gray color, whatever it is. So that is your the response of this. So this one, right? This green is this, which is this. So this is the response of G21. That is your pole which is closer to your imaginary axis, and G22, which is the light brown color. Okay, and if you see, so this is my settling time. So this is the settling time is 3.83 seconds for G2, and this is the settling time for G22, which is again almost 3.84. Okay. And if you take the peak overshoot is for G22, that is your the second order system is 0.023, and for this G21 is the G2 is the overall system, which is 0.024. So it is almost following. This is your overall response is almost or 99.9% matching with your second order, the pole which is closer to your imaginary axis. So that is your dominant pole. So this is the dominant pole. G22 is the dominant pole for G2. Okay. So G22 is this the real axis pole. Okay, fine. And the advantage of this, the concept of this, we'll see next. Okay, fine. And now let's get into the state space analysis, which is of course the x dot of x plus bu, y equal to cx plus du, where x is your state vector, your e is input vector, y is output vector, a is input matrix, a is system matrix, b is input matrix, c is output matrix, and d is transfer matrix. And for all practical cases, c will be almost zero because d couples your input and output directly, which should not happen. That d is almost zero for every purpose. And this is the block diagram of your state space system, a given state space system. By default, your state space system is an open loop system because there is no feedback. Okay, this only this. If you take this is only internal. Okay, and this is not a feedback of signals. This is for realization of system. It is not feedback. No signals are feedback. We try to realize the system, so you cannot claim this as a feedback. So you see no variables. Feedback in the sense that should be taken back and compared with the signals or input signals in general. So no, neither output nor other states are taken back and compared with you. So by default, a state space system is an open loop system. Okay? So this diagram is tells that. And coming to, I'm not going deep into that analysis of state model, and let us compare it to the controllability concept. So controllability, if you say when the system is completely controllable, okay, say a system is having some n state vectors, and you have say 2 inputs or 1 input, whatever it may be, okay. So if you are able to influence all the state vectors, all the n state vectors, if you are able to influence all the n state vectors by applying a controlled input, a control vector, because it is shown on one input, it is a control vector. By applying a control vector over finite period of time, then the system is said to be completely controllable. In the sense, by giving an unconstrained input, you should be able to influence all the states, maybe directly or indirectly. In the sense, your input may influence your state variable directly or it may indirectly. For example, if you give an input u, whether u1, that u1 may disturb say x3, x3 in turn may disturb x1, x1 in turn may disturb x4. Okay, so like this, x4 is also getting affected by the changes in u. Because either directly or indirectly, if you are able to influence all the state vectors by applying a control vector, then the system is to be completely controllable. Again, a state variable may not be affected by one input. There are more than one inputs, but if it is affected by the second input, that's also good. Okay, so one way or the other, by applying an input, you must be able to influence the state vector, all the state variables. That is called your controllability. Okay, that's the general definition is given out here. And how to make whether the system is completely controllable or not is by the help of the so-called controllable matrix, which is given by M into B, A, B, A square B, where A is your system matrix and B is your input matrix. And another concept is called observability, which is also equally important. But for this presentation, let me skip this observability. Okay, let me give an overview. Observability means, so in practical systems, you may not be able to tap all these state variables. The reason is, one thing, the state variable may not be available for measurement. For example, if you take your DC motor, say your EB, back EMF is one of the state variables. We can never measure your EB. That's known, am I right? So that is not measurable, number one. And the second cause is the sensors are too costly to measure it. Okay, a sensor which is available to sense a particular state variable may be much costlier, and you may not be able to afford it. That is second case where you cannot go for direct measurement of your state variables. And the third case, the measured state variable may be polluted by noise, which is unavoidable, maybe due to the inherent nature of the system. The measured state variable influenced by high noise. So it is very difficult to filter out a noise because we will not know which one is the noise signal, which one is the actual signal, and parameter signal. And also we may not be able to spare our time and energy to identify which one is the correct signal, and by applying different types of filters and all, again that's ruled out. Okay, so in those cases, but of course, output is always available. Whatever be the system, if you give the input, output should be available. Otherwise, we cannot take it as a system. So output is always available. And in most of the cases, output will be one of the state variables. You can recall that output will be one of the state variables in most of the cases, though it is not mandatory. So if you always our output is available for measurement. So by measuring the output over finite period of time, if you are able to estimate all the state variables, then the system is said to be observable. Okay, by measuring the output for a finite period of time, if it is possible to extract the information or estimate all the state variables, then the system is completely observable. So it is only possible when your output contains the information about the states. Then another issue, I will not go into that. Okay, so why we do this is the next concept, what you're going to see, the state feedback. So if you want to have successful or useful or efficient state feedback, you must be able to get all the state variables so that you can implement the state feedback control. But as I said, because of one reason or the other, the state variables may not be available for feedback. In that case, we go for observers, state observers, maybe full order observers or reduced order observers. Full order observers means whether it is available or not, we are going to estimate the state variables. Reduced order observers, we measure only the state variables which are not available for measurement. Okay, you can go for either one of this. And we get the state variables from the output. We measure the output and we estimate the state variables. And these estimated state variables are used for state feedback. Okay, that's enough. Okay, I'll go to next. And this is called the state feedback scenario. Okay, so now this 1/s integrator and all, this is based, which one is in gray area is the normal state model. And what we have done, we have taken all the state variables, okay, and we multiply it by a constant, then okay, and we add it with your input or to get the input for your state model. Okay, R is your reference input, U is the input for the state model. In the previous case, okay, not previous case, so U is R minus K into X, right? So U is R minus K into X. So this structure is called state feedback control. Okay, and normally there are two types of controls as you're aware of. One is called tracking and another one is called regulation. Okay, tracking in the sense when the input is changed, output is also changed. It has to follow the input. Output has to follow the input. For example, when you drive a car, if you give more throttle, the car should move fast. And when you apply the brake, the car should come down. And similarly, that's called your tracking. And regulation, if you take, and you say you might have come across the voltage regulators 7805, 7905, 7812, and all. So these voltage regulators are fixed at the output end of your rectifier. So this voltage regulator input may be fluctuating. There are two things. Input may be fluctuating. There are input perturbations, and there may be changes in output load current. Irrespective of the input perturbations and output load current, the output voltage should remain constant. In the sense, you are regulating it, right? So that's so there are two major classifications of control systems. Now, what you see right now on your screen is a regulator problem. Okay, because there is no input, and we try to maintain the system output, which is Y, which is not here, of course, Y, to meet our specifications. Okay, that's what I want to hear. And when you apply your mathematical knowledge, your x dot, your r equal to 0, so e equal to minus k into x. Okay, the previous case it is C. So it is minus. So this minus is brought and put over here. So this will be plus. So R is 0. So having that in mind, if you see this, you can get this block diagram. So when you do simple mathematical operations, what you get will be x dot equal to A into x plus B into K into x. This is very clear from this figure. So I can say A minus BK into x. Okay. So this is the equation of the state feedback system. And there is no input. So input is missing. So it is an autonomous system or the unforced system. That is the right word. This unforced system. So the roots of this are the eigenvalues of this A minus BK are going to determine the system response. Eigenvalues are, of course, are nothing but the roots of the denominator polynomial, or the eigenvalues are the poles of the system. And this is a very simple concept. So eigenvalues are the eigenvalues of A minus BK are the poles of closed loop poles of this feedback system. The system has become feedback. Earlier I said it was an open loop system. Now with the help of this, it has become closed loop system. Okay. So now A minus BK dictates the response of the system because the A minus BK, the roots of A minus BK are the poles of the system. The poles determine the system response, and so A minus BK as a whole determines the system response. So A is fixed because the system matrix we cannot change. B is also fixed, which is output input matrix which we cannot change. So the only available freedom is in this parameter, which is K. So by properly selecting K, we can make the system to comply with our specifications. That is the objective. Okay. So if you want to apply the state feedback, the one condition is, as I said, all the state variables must be available. In the sense, the controllability matrix M, what we have seen here, the controllability matrix M, the rank of this should be equal to the number of state variables or the rank of your or the order of your A. Okay, so that is the first condition. Only when this is satisfied, you can go for the state feedback control. Okay. So now we have our system and we have certain specifications. Okay. Now we have to design our state feedback control so that the system comply with our specifications. So as I said, from the given specifications, we can decide where the poles should be, and for that poles, we can generate our K. That's what we are going to see next. Okay. So the first one is to determine the values of K or the state feedback matrix K. That's called gain matrix also. That's feedback gain matrix or state feedback matrix. So which are calculated using the coefficients of the given system and the coefficients of the specified system. Okay, what system, how the system should respond. Okay, so when you have this, you can easily get this by using your SA minus A, right? SA minus A. So this can be obtained by SA minus A, where A is your characteristic, sorry, A is your given matrix, capital A I'm talking about. Capital A is your system matrix. By doing SA minus A, you will get this equation. So this is your, for example, I have taken a third order system. So for third order system, this is your I mean, from the given matrix, from the given system, we can get this characteristic equation. Okay, so we are concerned about these coefficients A1, A2, A3, and from the desired for the desired system, we have to get the characteristic equation. For the given specifications, we can decide where the port should be, and the ports we can get mu1, mu2, mu3, and from this we perform S plus mu1, S plus mu2, or S minus mu1, or whatever it may be, and we get the characteristic equation of the desired system, and the coefficients are given as alpha 1, alpha 2, alpha 3. If you know this, your k is given by this alpha 3 minus a3, alpha 2 minus a2, alpha 1 minus a1. This is the K matrix of your system. This is one of the methods. And the second method, of course, the equivalent MATLAB command is K equal to place A, comma, B, comma, P, where A is your system matrix, is n by n matrix, B is your n by 1 matrix or one single input system, P is the poles where you want to have your desired system, how the system should respond. So this is your MATLAB command to implement this method. And the second method is called Ackermann's formula, which is given by, for a third order system, 001 M inverse into phi of A, where 001 is the matrix. Okay, so Ackermann's formula, which is given by K, and this is your normal row matrix. M is the thing what we have seen earlier, that is your controllability matrix, that is given by this. So this is your, this is what you see, this is your M. So you can get your M. So we have M, and then finally we have your phi of A. If it phi of A is, so this your characteristic equation of the desired system, what we have seen here. This is the characteristic equation of the desired system. This last one, S3 S cube into alpha 1 S into alpha S cube on S square, because I'm sorry, S square is missing here. This is S square, alpha 1 S square plus alpha 2 S plus alpha 3. So you substitute your A here, okay? That is your phi of A. Okay, so when you do this, you will get your K. It is a bit complex mathematically, but there is a simple method in MATLAB using this Acker formula. Again, the parameters are A, B, and P. But instead of place, you give Acker. So you will get your K matrix, and once it is there, you will go for it. And this is a simple example what I have taken before going for the actual implementation for electronics. This is a simple matrix. So this is in controllable form, so there is no need to check your controllability. And so for these two systems, the SA minus A, and this is this is the characteristic equation of the given system. So A1 equal to 6, A2 equal to 5, and A3 equal to 1. And now let's take the research system. So the given complex specifications are zeta should be zero point 0.5 with the sampling time of 2 seconds. So sampling time equal to 4 base zeta omega n. 4 base zeta omega n. So on omega n, zeta equal to 0.5. From these two, I can get value of omega n equal to 4 radians per second. So dominant parts will be minus zeta omega n plus or minus the omega d, as I said, the real parts of the pole. Okay, so which is at the minus 2 plus or minus j23. So now we have concluded when the poles, complex poles are this, I'll get this specifications. I'll comply with this specification. Okay, so I have to take my third pole because the system is third order. So I have to take third pole at 5 to 10 times to the right of, to the left of my available poles or complex pole or dominant pole. So which is minus 2. So I have selected minus 10. You can take anything between minus 10 to minus 20. You may ask, why can't I have minus 50 or minus 100 or minus 200, wherein the response or the contribution will be almost zero. But when you have your poles farther away, very farther away over your left of the S-plane, the system will be highly prone to your noise. You can see that when you take your Bode plot, after once it crosses 0 dB line, and after 3 dB on your bandwidth, sorry, not bandwidth, after 3 dB line, it has to fall sharply. But when you have poles further away from your imaginary axis, it will be somewhat lesser slope. So it will be highly prone to noise. So it is not advisable to go for poles with higher negative real axis. Okay. So this I have got mu1, mu2, mu3. So when you do your this process, mu1 n into mu1 plus s into mu2 plus s into mu, because this does become plus because this value is minus. That's why I said this is minus or plus. So this is what I get. So this is the characteristic equation of the desired system, from which I can say alpha 1, alpha 2, alpha 3, which is 1456 and 160 respectively. Okay. Now let me go and check the performance with the MATLAB. So let me load example 3. Example 3 is loaded here. So this is my example 3. No, this is my example 3. I have got A matrix, which is 0, 0, 0, 0, 1, minus 1, minus 1, minus 6, B equal to 0, 0, 1, a column vector. And this I am doing this process. I do not want to go deep into this. I'm converting this for printing process. And this is the initial condition what I have assumed. Of course, this was taken from Agatha. You can refer to that. And I have extracted the state variables and I'm plotting it. This is for uncompensated system. And the second one, second plot. So here I'm finding my k value using the place command. My poles are defined here. P is equal to minus 2 plus or minus j 2 root 3 and minus 10. Poles are defined here. And I'm calculating my k. And I'm defining the desired system, or which is what defined as my system and all. And this is over here. Let me run this. Okay. Now, if you see the plot, where is the plot? Plot is missing. Just a minute. Let me run it. What's the plot? The plot is missing. Okay, let me try with this. There is an error. Choose minus. So it is not running. So this is what I, please hold on. So fine. So there is an error. So let me correct it and send it to you later because I have no time to correct it. So fine. So this is how we design our systems. This will work. This will work. I'll show you if time permits after some time. Let me go get into that major thing, which is design of how to design your all-round circuits using this. Okay, so this is the circuit, very simple circuit, which is for your single phase, full bridge rectifier. Okay, H bridge rectifier. This is your single phase rectifier, and this is your PLL to generate your signals, reference signals, and this uses this T and gives your reference signals, and that is given to your thing, and this is all this LC filter, and this is your grid connected load and all those things. And if you run this, it's getting compiled. Let's wait for some time. So 50, 70%, 80%, 90% is over. So if you see, this is the response. This is the response of the system. So I have defined for, so this is the response. So this one is your, that is your grid voltage, inverter voltage, grid current, inverter current. Okay, these are all 4 parameters. Grid voltage, inverter voltage, grid current, inverter current. Okay, and this is inverter current. This is a grid current. This is a grid voltage, and this is your inverter voltage. This is what I get. I'm not concerned about this. Let me take the pulse. So if you take the pulse, okay. And this is how the pulse look like. Okay, okay, this I think you're all aware of. So this is your triggering pulse. I am concerned about this triggering pulse. Okay, now what I have done, I have so you take this circuit. So it is same. It is similar to your previous circuit, except that I have used the state feedback controller. This is the state feedback controller, which I have used here. This is your previous one. It is still there. This circuit is intact. What I have done is I have added this to this thing. Okay. Now the pulses are generated. See, the pulses are coming over here. Okay. This is your given to your PW inverter. Here it is given from your previous controller. Here it is given from, this is your PID, sorry, your state feedback controller. And this is your control gain matrix. So this is where you're supposed to enter your matrix values, K values, and all those things. Okay. I haven't designed it because I was to design these values this morning, but couldn't because of the known reasons. So this is by default you're having something, and let's see what it comes, what we get. So now this I have taken the state variables directly from the system. Okay, here what is my state variable? Here I have taken the grid variable is sorry, not grid variable as the reference. Okay, we have to give the reference. The grid variable is given as the reference. This is your R input, and the state variable X and the output are my filter outputs. Okay, so that is your H bridge inverter. Then you have LC filter. The output of the LC filter, the voltage is given as my output and also the state variable. Okay, I have taken only one state variable in this case, and let me check the pulses. So this pulse, the first one or the second one, is derived from the previous generator, and the current one, this is from the state feedback controller. Let us see what is this. Okay, so if you see the small period, let's take any small period. Is it over or not? So you see, these are also, the top one is the pulse generated by the state feedback controller. The bottom one is the pulse generated by the previous system. So these both are almost same. The both are almost same. Even you can even enlarge it, and you can see almost same pattern is coming from your previous PWM controller and also state feedback controller. Okay, there are certain issues, as I said, I couldn't correct because I had no time. And the next one, what I have taken is, I have taken both, I have taken only the voltage. The second case, I have taken both the voltage and current as the state variables. This input, here you can see there's a multiplex available from which I have taken the output from the current output and also the voltage output of the output after the filter or the thing which is coming out of my HPH inverter. The current and voltage both are taken and fed as the outputs and also as the state variables. Okay, this is what I have done here. And let me run this also and see how the pulses are generated. And again, if you take this scope, the one of the inputs is from the pulse, the previous pulse, and the second one is the pulse what is from my state feedback controller. So if you inside the state feedback controller, you have the state feedback matrix K. So you have to take your X, Y, or your current or voltage, whatever it may be. You decide how the output should be. There should be any overshoot or there should not be any overshoot. And what should be the settling time. Everything you can decide based upon that, and applying our previous technique, you can decide what's your K matrix and enter this K matrix in this block, what is over here. And then, and once it is done, and we can do all these interconnections and check the results. Okay, the overall performance I'm yet to analyze, but I didn't. But however, I was successful until this generation of pulses. Okay, let me check the pulses. This is the comparison of the pulses from previous one and the pulses from the state feedback controller. These two are the things. Let me have this. Okay, now let me check small portion. So what you get will be almost same. Okay, let me give in smaller versions. Okay, even just hold on. So small variations, right? There are small variations between the previous and current one. We have to sit and analyze. Okay, here you have a better width of pulse width, and here you have lesser pulse width, and this pulse width and this blue and blue, red and red are a bit higher in our state feedback case. And the performance we have to see. As I said, I had no time to analyze the performance. So when two parameters are included, when I included current also, there is a change in the triggering pulse. So it may further improve this system performance, which is left for analysis. Okay. So likewise, so that's objective. So likewise, you can select your state feedback controller, decide what are all your feedback parameters, and what should be your performance criteria, and based on that you can select your K matrix, design your K matrix. So check enter the values of K matrix over here, and then you can run this. Okay, so this is a good idea about designing your state feedback controllers for your power electronics applications. I'm not good in power electronics. Had I been good, I could have solved all these things. So I was also struggling some time back to get this output. So I was halfway through only, honestly speaking. But I'm sure that if you proceed, definitely you can get a better approach using the state feedback controllers. Because if you see the research articles, to the best of my conscious knowledge, only lesser articles are available based on state feedback control. But if you take your MATLAB and if you go refer your examples, so go to your reference section, if you go for examples, there are plenty of examples given to make your torque control, to make your speed control. There are 20 or 30 examples are available using your state feedback method. Okay, so you can refer to those methods. It is still a powerful method, and you can try implementing this state feedback method for one of your proposed systems and check the analysis. And the advantage of this is it is much simpler than your complex this system. So you have to measure your omega, you have to modulation index and all those things. You have to decide that is you can overcome those complications, and you can decide your a better state feedback, a better controller using your state feedback. That's all from my side. So with this, I couldn't fully because I had one more item also, that is how to develop your state model for your single phase full bridge converter. How to, yesterday I had a discussion with R.B. Selvakumar sir. He's one of my scholars pursuing PhD, and we have seen how to develop the state model. So from the different sections, we calculated the current and voltages. From those, we developed a block diagram model. From the block diagram model, we developed the state model. The one thing where we left out is this firing circuit. Okay, that could be obtained from this part. Okay, so that barring that, we have all completed the design of that, but we couldn't present because of the time constraints and other issues which are coming over to me. So with this, I thank the participants for their passions hearing, despite my interruptions due to their own reasons, because Sindhu Sir's was calling me in between. I had to attend that also. And despite all my odd things, I have made a presentation which may not be as per your expectations, which may not satisfy your expectations, but very sorry for this. But I have done my duty to the best of my knowledge. Thank you very much, please.
Thank you so much, sir. Thank you so much.
Thank you, sir. Thank you.
Sir, questions?
Please. Yeah, questions.
There are some questions in chat box, sir.
Chat box. Okay, let me check the chat box.
Okay, sir. First question from Armuga Babu, sir.
Please.
Why we are preparing unit step response in control system, then other inputs like
okay,
RAM?
fine. It's a nice question. So if you take your inputs, there are 4 standard inputs. That is impulse, step, parabolic, and ramp. These are all the 4 inputs. And if you take impulse, it is 1. If you take Laplace transform, and if you take step, it is 1 by s. Ramp, it is 1 by s square, and parabolic, it is 1 by s cube. And if you want to test a system, obviously you may have to, because if you take any practical system or any practical input, you can classify the practical input as the combination of these 4 inputs, okay, or one of the inputs or combination of these 4 inputs. So if you want to analyze a system, our analysis is meant only for linear systems. So you can, with the 4 different inputs, you can analyze the system, and you can add the responses of these 4 inputs to get your overall response. That's what we normally do in this linear system analysis. So it is highly time consuming and not possible to test your system response with all the 4 inputs. So if we, and of course, if you take your impulse, step, ramp, and impulse, if you take impulse, it is 1. If you take ramp, it is 1 by s. So in Laplace transform, 1 by s is integration. So if you integrate impulse, you will get your step. If you integrate your step, you will get your ramp. If you integrate ramp, you will get your parabolic. So 1 by s, 1 by s square, 1 by s cube. Okay. So just take response of one input, and you can integrate or differentiate to get the response of other inputs. In this case, your error coefficients, that's position error, velocity error, and acceleration error coefficients. These coefficients are come in handy. So you take the response of one of the inputs, and you can analyze the system response for the remaining inputs. Out of this, a much simpler and more practical input is to a step. That's why we go for step.
Thank you, sir. One more question, sir.
Please, sir.
From Sarananji. Very good afternoon, sir. We are using MATLAB software for control system concept simulation. Is there any other software tool is available to simulate the same?
Look, sir, LabVIEW is also available. LabVIEW is one of the powerful software, but then may not support directly your control systems, but it is meant for control. LabVIEW, to the best of my knowledge, LabVIEW is another powerful system. I know only these 2, sir.
Okay, sir. Okay, sir. Thank you, sir. There are a lot of messages in chat box. The wonderful session, particle session. There will be given nice feedback when the chat box itself, sir.
How to see the chat box, sir?
Sir, in so right and
Oh, okay, got it.
count it was 89 nearby.
Okay, okay, sir. Thank you, sir. Thank you. So, once again, I thank all the participants for their tolerating me for my interruptions, and I thank the organizers for this wonderful opportunity. Thanks, and have a nice day. And as I said, please stay safe. That's very important. Thank you, one and all.
Okay, thank you so much, sir. Karunya.
Yes, sir. On behalf of Dr. NGP Institute of Technology and Department of Electrical and Electronics Engineering, I give a really heartfelt vote of thanks to the resource person, Dr. C. Vivekanandan sir, for sharing his thoughts, which will be definitely encouraging us in our future events. Sir, your thoughts have enlightened our mind. Thank you, sir, for your precious time and thought-provoking presentation. Thank you, sir.
Thank you, sir. Thank you.
Thank you so much, sir.
Thank you, sir.
Participants, kindly fill the feedback link posted in the chat box.
लेट जा मैं तेरे को पूछा मैं क्या लेटी जा तू जवाब क्या दे दी पर सुनी तो लग रहा कर बंदा मैं क्या लेटी जा तू भी आके कुछ और मैं लब गई पूरा लफाफा देना ना पूरा लफाफा खाई होना है चक्कर पारे दा